So this video, we're going to talk about chapter 4 in the textbook, and this is the microarchitecture level. Okay, so as far as how to use these videos, what I'm attempting to do and how to kind of prepare for this class, a lot of what the textbook covers is of a technical nature, and it's not really something that I can lecture effectively about. So it really comes down to having to do a close reading, more than likely at least 2 close readings of the textbook in order to understand what's going on. Okay, so make sure, I know for me, I always do one quick read through to get the overview lay of the land, and then I'll do a more detailed reading trying to work out all the examples. Okay. I also wanted to kind of situate us here in this level. So we talked in the last video, chapter 3, about the digital logic layer, okay, or the digital logic level. At that level, we're talking about the physical hardware components, okay, the integrated circuits, and then which are made up of the different gates, the AND gates, or typically the NAND and NOR gates because they take less transistors. So the reason that we have the levels that are on the screen here is that it's not efficient to do any kind of programming at the digital logic level. I mean, you could, but it depends on the exact same hardware, the exact same CPU, the exact same memory in the same address, the same configuration, the same bus, the same everything. Okay. So in addition to dealing with a language that is not particularly expressive, you're also dealing with the fact that you could only have one kind of computer, or you would have to rewrite your programs every time. Okay. So as we're moving up, we're getting to the point when you get to level 4, for example, the assembly language level, you're then able to operate on a whole range of computers. Okay, so you've gone even at the operating level at level 3. If you write a program for a Windows computer or a Mac or Linux or whatever you've got, or an iPhone, you don't have to worry about, in fact, I bet you've probably never worried about the kind of memory your system has, or the exact CPU that it has, or any of that. So we've abstracted that out. So as we go up from level 0 to level 5, we're more abstract, but we're also able to have a much wider range of devices. Okay. And typically what happens on the chip itself is that, of course, the level 0 is just hardware, so it's going to be there. The microarchitecture level, which we'll talk about today, its main purpose is to branch between the digital logic level and the ISA, or the instruction set architecture that's above it. Okay, so all of this is going to be on the chip itself, okay, in ROM, read-only memory. Okay, the operating system then will be installed above that. It's often in ROM as well, but you've got some options there. And then as you go forward, okay. So that's why if you're writing in Python, for example, at level 5, you don't care any of that. All of it's been abstracted, okay. But it's been abstracted because somebody has bothered to create for every bit of hardware, this microarchitecture, this instruction set, the operating system, the assembly level language. All of that is assumed to be in place. Okay, so that's kind of what's happening there. Okay, and the other thing to talk about before we get into chapter 4 in particular, and again, I'd mentioned techniques for using the videos. To me, I think it makes sense to listen to the video before you read the chapter, and then maybe again afterwards. Okay, and the real test of your understanding is, are you able to do the homework problems, and are you able to do them correctly? If you're able to do the homework problems correctly, then you're understanding what's going on. If not, you're not, and it's worth taking some more time and asking some questions. Okay. So the other thing we want to talk about here is RISC versus CISC. So remember, the RISC is the reduced instruction set computers, where the CISC are the complex instruction set. And if there's a chip that follows the super rigorous RISC model, okay, it means that for every command that the hardware does, there's exactly one command at the microarchitecture level, and there's one command at the instruction set architecture level. Okay, so that's really where the RISC comes in. There's a direct translation, okay, 1-to-1. Okay, where on a CISC system, even at the microarchitecture level, it will probably have many digital logic level commands it will do. The ISA will certainly have more and more and more as it goes up. Okay. Pros and cons there. Okay. The pros of a RISC architecture is that it runs faster. It doesn't need that quick translation. It's a direct, quick table lookup. Okay. The disadvantage to a RISC is that the language is not as rich. You have to write more commands in order to make the same program happen. Okay, so that's kind of where that's at. Okay, so now let's talk in particular about chapter 4. Let me make sure that I actually have that shared. You're not having to look at me the whole time. Okay, so again, the microarchitectural level, it says it right here. Its job is to implement the ISA and the level above it. Okay, and that was my version of that figure 1-2 that you're just looking at. Okay, so what they're going to do here, they're going to explain this with an example, because there really are no general principles. Okay, every time we create an instruction set architecture, it's a special case. Okay, and again, what we're trying to get to is the next level, which is an assembly language level. Okay, or actually, I guess the OS is next, and then the assembly level. That's what we're trying to get to. So each level strives to get you to the next one. Okay, so they go through this example here of creating a subset of the Java virtual machine that contains only integer instructions. Okay, which simplifies it. And they go through that example a fair bit, talking about some way things work. Okay, so it's important when you look at a diagram like this one, this is figure 4.1, that after you've read it, you kind of understand what's happening here. Okay, so it gives it some labels here, but it's going to tell you more in the text. Okay, so in general, up here we have our different memory control registers, and then we have our control signals. Okay, for any of these systems, to make it work, you have to think about what are the control signals and what can we do with them. So we see here we have our enable onto the bus B, which goes this way, and then we have our write C to the bus. Okay, so the data flows in this way, out that way. Okay, and it all comes down into this ALU, our arithmetic logic unit, and then there's a shifter control here. Okay, and that's the basic flow of things as things come from memory. And here's our program counter and some other things that we're dealing with here. Okay, so again, when you see the slash line, it means there are more than one, but they're not going to draw all the arrows. Okay, so it's important to kind of track through how these things tend to operate. Okay, so here's an example, the different combinations of the ALU signals and the functions that are performed. Okay, so we have all of these enable A, enable B, all these invert A, all that. And this is what gets us to our functions for our ALU, okay, for this particular example. Okay. We then talk a little bit about the timing here. It's important on each clock cycle that things happen in a certain sequence. We talked before about the clock and how that works. Okay. This talks about the memory that we have. Okay. In this case, we have a 32-bit address bus. So, and that 32-bit address will tell you how many memory values you can store there. Okay. Or how many can be addressed with 32 bits. Okay. And then we talk about the micro instructions from that figure. Okay, so there are 29 signals. We have 9 signals to control writing data from the C bus into the registers, then 9 more to enable the registers onto the B bus, which goes directly into the ALU input, 8 signals to control the ALU and shifter functions, and then 2 signals, which we don't have shown, indicate the memory read write. That's the MAR, MDR stuff. Then 1 signal to indicate the memory fetch, okay, via the PC and MBR, okay. So again, goes through more on the example. Here's the micro instruction format. Okay, so this is what in binaries, zeros and ones, this is going to look like when you send those. Again, these bits are literal bits. 1 means they're on, 0 means it's not. Okay. And then it just explains more of how that works. Okay. Then we next get to this MIC1, the micro instruction control language they're creating as an example. Okay. It's 1 because we're going to add some detail to it. Okay. So again, it goes through here. And this is the complete block diagram of this example microarchitecture, the MIC1. So what we've added here, okay, we've added the decoder to deal with the memory addresses. We've got the memory over here, okay, where the microprogram is going to be held. We've got all of the control lines going back and forth. Okay, so we solved this before, more or less. So this is adding the rest of the system. Okay, so again, it's important to read through and to follow through those different different lines to see how they work. Okay, so more detail on that. Okay, here's an example again with the example ISA on this IJVM. Okay, we're going to call that again at the level 1, which we're at now. We call it a microarchitecture. When we go up to level 2, we're going to call it the macroarchitecture. That's the ISA level. Okay, and it just talks about how we can use stacks for our commands, how those things work. Okay, and again, there's the memory model for our example. Again, all this is not anything real. This is just an example. Everything that we do is going to be different. They're all special cases. Okay, so more stuff there going on with that example. Okay, we then go through how we could take a Java program, okay, and compile it onto this integer Java virtual machine that we've talked about. Okay, so we start over here with a fragment of some Java code. Okay, we then have what the assembly language, not to the right, this middle stuff, is what an assembly language program for the Java virtual machine would look like. Okay, so you see that these few instructions lead to a lot more instructions here. Okay, and then the actual program itself then will be in hexadecimal. This would what would run at the MIC1. Okay, so read through those examples, make sure that that makes sense to you. Okay, so then we're going to look at so we've both got the microarchitecture and the macroarchitecture, so we have to implement it. Okay, so how does a program running on the microarchitecture get interpreted into the macroarchitecture? Okay, so it's going to give us some examples here on how those changes are made. Okay, so again, it goes through some more on that. Okay, here's an implementation of the IJVM using the MIC1 machine. Okay, so it's going to go through with the code. It's going for each of the commands we have. So example for the add command. Okay, it's going to tell us what we're doing. We're going to read in the next to top word on the stack. Okay, H is the top of the stack. Okay, and they're going to add the two words together and write to the top of the stack, and then go back to main. Okay, so that's kind of the idea. So each of these sections between the lines are going to be an implementation of a different command. So we have the add, we have the subtract, we have the and, we have the or, we have the duplicate, we have a pop, swap, push, load, store, okay, and then some different wide one, wide two, all these different different memory address sizes, basically. Okay, and then we go on and have lots of other stuff, go-tos and lots of things. Okay, so you see there's a fair bit for that to get all of those commands. Okay, so there's an explanation there. Okay, and some more examples that we can do with that. Okay. Okay, so when we're designing the microarchitectural level, what we always get to is the idea of speed versus cost. Okay, so if you want it fast and cheap, you're not going to get it. Okay, that speed costs and pretty much whatever in life that you want to do. Okay, so speed can be a difficult thing. Okay, to measure, but there are three approaches we can use to increase the speed of execution. Okay, we can reduce the number of clock cycles needed to execute an instruction. Okay, so every instruction takes so many clock cycles to get through. If there's a way to make that go quicker and do more with less, that's a good thing. Okay, we can simplify the organization so that the clock cycle can be shorter. Okay, if you don't have to do as much per clock cycle, you can speed it up and have more clock cycles per minute. Okay, or you can overlap the execution of instructions. Okay, you can and do some parallelism there, so you can be doing more than one thing at once. Okay, so this section is going to go through some of those. Okay, so give you some examples here. Again, I'm not going in great detail because this you need to put into your brain yourself. Okay. And now they've introduced the MIC2 here, which adds some more this instruction fetch unit, basically, is, I think is what they've added there. Okay. Then they've got the pipeline design on the MIC3, okay, which adds an A bus to it. You see the picture down here. Yeah, that doesn't show the A bus, but there is an A bus there somewhere. Oh, yeah, we do. There's the A bus. Okay. Which again, we're adding some more to this to increase the speed. This time we have a 3 bus. Okay. And then we've got some more about that. Okay. And this is an example of how the pipelining would work. Okay. And then finally, we have, I don't think there's a MIC5. The MIC4 has a 7 stage pipeline. Okay. So there's more involved there. It's going to show some of those main components on how those work. Okay. Again, this is for our made-up example. It's just showing us how we could make it faster by doing these different techniques. Okay. In 4.5, we talk about, again, more about improving performance. Okay. Cache memory is one of the big things. CPUs didn't used to have cache, but they now do. So that cache is memory that is located usually directly on the CPU. The CPU can only really talk to the registers, but it can get to the caches much quicker. Okay. So this talks about the idea of caches, how those work. So here we have our CPU chip, and we have the unified L2 cache right there. Okay. You can also have another cache that's not on the chip. This is the L3 cache, which can also, again, it's closer than the main memory, and that's the point. Okay. And we've talked before about memory. The closer it is, the faster it is, but the smaller it is because the more expensive it is. Okay. So that's kind of how those metrics tend to go. Okay. So it gives us some more examples here on how that works. Okay. Another important thing on this pipelining, one of the problems you have with pipelining is that you start doing things that you think are going to happen. So you predict what's going to happen. Okay. So which branch to follow comes under this idea of branch prediction. The better you can predict what things to start pre-calculating or pre-running, the code you want to run in advance, the quicker it's going to be. Let's talk some about that. Okay. Okay, it also talks here about out of order execution, register renaming, some things that come in, other approaches that you can take to try to speed things up. Okay, we're still in the performance enhancement, improving performance here. Okay, so again, speculative execution again, where you can go ahead and execute something to have it pre-compiled, ready to go, and hope that's the right thing. If not, you've wasted the time. But hopefully overall, if your branch prediction is good, you'll increase performance that way. Okay. We then have our examples from our different systems. Okay. So this is the microarchitecture of the Core i7. Super complicated. This was the Sandy Bridge microarchitecture, which was an Intel family of processors that used for a while. Okay. Here's a block diagram, kind of how things work with the caches. Okay. And all of that stuff. Okay. Yeah, and it's a super complicated processor because it's fast and it's just gotten worse. Okay. So it's going to go through, give you some examples there, how that works. Okay. The next thing it's going to do is the ARM chip we've been using. Okay. The system on a chip that we're talking about here. Okay. So it's going to go through, and again, the ARM is going to have a less complicated system. Okay. And it says this bridges the gap between RISC and CISC. So it's reduced compared to a CISC system, but not as much as a full RISC system would be. Okay. So it's going to give us our examples through there. And then finally, we talk about the Atmega 168 microcontroller, which is much simpler. Okay. And it's going to give us how, what this looks like, basically. Okay. How it's implemented. Okay. There's a comparison here of the i7, the ARM chip, and the Atmega chip, where it talks about, and then a summary of the chapter. Okay. So that was a pretty brief overview of a lot of material. Okay. So again, hopefully you'll watch the video first, you'll read the chapter, maybe read it again more closely. Again, I do a fast reading and then a more slow reading, and then watch the video again if you need it to make sure you're understanding the bigger concepts, and then look at the homework. If you're getting the homework, then you're on the right track. If you're not getting the homework, then you're not understanding things properly. Okay. Okay, so that's it for chapter 4.